Hello everyone, my name is Jaquez Johnson. This is our final lab, Lab 5, Magnetic Molasses. So a quick introduction. In this lab we explored Faraday's law by studying a falling bar magnet and a conductive roll of aluminum. And we used the Faraday's law to understand how the dB/dt of the magnetic field induces currents and forces. Moving forward, the important formulas and concepts used. Of course, we had Faraday's law, which is a changing magnetic field through a closed loop induces a EMF. We have Biot-Savart law, which we used in Lab 3. Two more laws. We have the Lenz's law, which gives us the direction of an induced current. We have Newton's second and third law. So for our system and surroundings, our system was the falling bar magnet and the induced currents created in the aluminum tube. And our surrounding was the air around the system, including Earth's gravitational field. Just for a quick preview, our computational time was about 1.2 seconds. On the other hand, our experimental time was about 1.35 seconds. So getting into the experiment, quick walkthrough, we marked the north pole of the magnet using a magnetometer on our phone. We dropped the magnet through the tube. We recorded it entering and leaving the tube, and then we calculated that average time. Some initial conditions. Our aluminum foil roll was about 1.7 centimeters thick. We had 0.0025 kilogram magnetic mass in a radius of about 0.02 meters, and our total roll length of 0.3 meters. Here's a picture of our setup. On the left, you can see us dropping it, and then the bar magnet, and then you can see on the right the bar magnet leaving the tube. Here are the experimental results. We did 5 trials, and we took the average, which was 1.348 seconds. So the checkpoint questions, why can't we use a ferrous tube example like a steel pipe? The falling magnet would magnetize a steel pipe, and that's going to create additional forces, which alter the behavior of the induced currents. What happens to the magnet as it goes down the tube? The changing magnetic flux induces currents, which then oppose the magnetic fields, and then that affects how fast it falls through the tube. So getting into our computation, a few code points that I want to point out. One, we have our mu magnitude, which we calculated from Lab 3. We used the same exact magnet. Moving forward, we visualized the bar magnet. Here are some things that the code did. The next was defining the dipole of the B field, and that's just copying it from Lab 3, and we made a function for that. Next, we created a function for calculating the change in magnetic flux. After that, we calculated the force of gravity, which is just negative mg. Then we calculated the ring current by setting it equal to negative ddt times 1 over ring dot r. Next, we set the magnetic force to just be in the y direction, in the positive y direction. And then we took the F-net, which is just adding the force of gravity and the force of the magnetic fields. And then in the last step, we calculated the bar velocity and position for our velocity versus time graph. And here's that graph. As I was talking about, we initially see the steep decline, then it starts to kind of plateau as it leaves the system, and that's as the fields are getting stronger. Here's an example of the visual, and then also the resulting 1.88 seconds for the time that the magnet was in the tube. So our findings and our conclusion, some potential errors were the experimental setup. So maybe the magnet was not dropped perfectly along the central axis of the tube, or we just inaccurately recorded the times. Also simplified assumptions. So we assumed the tube was perfectly uniform cylindrical, and that it was constant in thickness and resistance, which we know it might not always be true. But that's why there's a difference between our computational and our experimental calculations. So addressing our additional questions, what if the resistance of the conductor were reduced as close as possible to 0? We know that the induced currents would increase significantly due to Ohm's law. That's going to be EMF is equal to I over R. So if our R drops, the induced currents would increase. So that will, as a result, increase the fall time. So what if holes or slots were cut into the tube? The magnet would fall faster as there's disruptions in those loops. And then again, the disruptions would weaken the currents because the closed loops are required for the formulas in Faraday's law. So a quick conclusion, the simulation modeled the magnet's motion through a conductive tube using Faraday's law, and there were discrepancies because of idealized assumptions, measurement inaccuracies. And then lastly, the factors all come together to highlight the complexity of real-world observations versus just simplified computational models. Thank you.